Okay, so thanks for coming to the museum today. My name is Mark Taylor, and I run the planetarium here, but I also do the other science programs. So we've done things like gone down to the river and do seining and catch silver sides and things like that. We've gone up into the woods and collected leaves and analyzed them. And one of the things that we have here at the museum, which is closed at the moment, is an exhibit which is all about the Hudson River. So because that is closed, but because we do still want to have ecological issues addressed here at the museum, I decided to invite Dr. LeGrande here to come and speak. Now, she's been here before. There's some other things that we've worked on. She came up and worked with the junior docents, our high school students before, and we did a workshop about isotopologs, which you can get into what those are. First off, just wanted to hope everybody could just welcome her real quick. And just a little bit about you specifically. I want people to listen as Dr. LeGrande speaks, because you'll be able to tell that you grew up in Texas.
Yes.
Comes out every now and then.
I have a couple slides left.
Right. Went to Rice University, and then from Rice University has been at Columbia pretty much since then, and working mostly at a sort of secret computer lab in New York City, which is kind of cool. It's a kind of place where some like Spider-Man villain would be like hiding out, programming something like that. It's kind of cool. So she'll go into that. But her work in general has been about climate modeling. And I wanted her to come today and talk about how that actually works, because you hear about those climate models, and basically it involves computer science, but it's a very specific type of computer science. And it also involves getting your hands dirty, working with things like core samples and air samples and whatnot. So if you want to introduce yourself any bit more, you can do that. But for now, I think we're ready to start.
Sure.
Take your mask off.
All right, I'm going to take my mask off if everyone's comfortable with that. If y'all keep yours on, then we'll all stay safe.
Can you hear her? You need a microphone.
Shall I use the microphone? Yes. Okay. My daughter tells me I should all the time. So glad. I'll let her know I need a microphone.
That's okay.
Okay. So, as Mark said, my name is Allegra LeGrande, and here I like to always start my presentations with this video that probably some of you have seen before. Every January we're talking about how warm it was last year, putting that in context of the historical period. And you often see some sort of figure like this. This is a product that's made at the NASA Goddard Institute of Space Studies, where I work. And it is a map of the temperature anomalies over the last 150 years. Now, what's a temperature anomaly? So this map is obviously not showing the seasonal cycle, how it's, it's hot in the summer and it's cool in the winter. This map is showing the departure from what it should be typically. And so what you see, this map is coursing this little 5-year snippets in time. The loop starts in 1880 and it cuts this 5-year average all the way into the present. And what you see as it rolls over in the beginning, everything is quite blue. We use a baseline period of 1950 to 1980. So in the beginning, things were cooler than they were then, and it slowly warms up. And spinning in the right corner is just the last 5 years, where it was quite warm. In fact, it was about a degree Celsius or 2 degrees Fahrenheit warmer than it was on average between 1950 and 1980. So the question, when today's temperature exceeds that which humanity has ever known, how do you even begin to address the problem? How do you characterize the problem? How do you put the problem into context? I like to, if I say something that you don't understand, we're a really small group, so please don't feel shy about jumping in and saying, what does that mean? And let's keep everybody together, so just feel free to interrupt if you need to. Yes, I am actually originally from Texas. I'm from Midland, Texas. Maybe somebody knows about a book or a TV show called Friday Night Lights. I went to a high school formerly known as Lee High School. We have now changed our name to Legacy, which was a victory for my classmates and I. And yes, my father's in the oil business. There's a pump and jack in the background. My great-grandfather's in the oil business, but when it came time for me to decide what I wanted to do for college, I decided that wasn't the right path for me. And my parents were on board with that. So now I'm a physical research scientist. My employer is NASA. I'm an adjunct at Columbia. I've lived and worked in New York City since 2001. Passed through Houston, where I did my undergraduate work at Rice University. So there's all the stamps of where I was and where I am now. So how did I get into studying climate science? Well, when I originally started school, I was really keenly interested in genetic engineering. I knew I wanted to be a scientist of some sort. It turned out for me, I didn't like being in a lab with the pipettes and dispensers and the pressure of like working with diseases, so I needed to do another kind of science. So I was reading books at the time like Jared Diamond's Guns, Germs, and Steel. One of my professors was an anthropology professor. Actually, as an undergraduate, I studied geology, geophysics, and anthropology. And my professor was really interested in how climate change might have perturbed societies and caused societies to grow, to shrink, to prosper, or to perish. And this idea was in line with these popular books. Turned out I loved computer programming. West Texas was not great about everything, but computer programming was one of the things which my public school system excelled in. And I was, my own children who are 10 and 12, they don't get much hardcore computer science, but for myself, we started learning QBasic on old Commodore 64s when I was in 4th grade. So that continued for me throughout elementary school and high school and college, and even today, where I'm still doing computer programming. I was also, interested in this intersection between people and the climate system. When I was in college, I did field work in Santorini. Santorini is a volcano that's partially submerged. It's in the Mediterranean, just north of Crete. And there was this really complex society there that was destroyed by a volcano. And they actually found this really interesting society when they were mining the pumice rocks there. They were building this out the Suez Canal, and they found their society. So it really got me thinking about how there's this intersection between climate change, between the way peoples develop, and this is how I merge geophysics and anthropology to be the climate researcher that I am today. So first, when I say climate, I don't mean weather, but what is the difference between climate and weather? So today, I see everyone here, we're wearing jackets, we're wearing sweaters. We knew that when we went outside this morning that we would need to have more than a t-shirt and shorts because it's still coming out of the winter season. And things that are on that seasonal scale or longer, that's climate, like that's what the climate is. Weather is, maybe tomorrow it's going to rain, maybe tomorrow it's going to snow. But if I were asked you to look at these two weather maps, I would say, hey, which one do you think is more likely for tomorrow? You would know what the climate is like. You wouldn't need to have seen the news this morning. You would say, hey, it's not going to be hot and humid with flash flooding all over the United States. That's not the climate this time of year. So that's the distinction between climate and weather. It's really a matter of scale. Just for context, I put this is what the climatology is for New York City. It'll be pretty similar for here for Yonkers. Green is precipitation. We have about 4 inches of rain every month, and then we have this nice seasonal cycle and temperature every year. This is the actual temperature in Central Park, and you can see that unlike the first figure that we have this big coherent picture of warming, starting out cool, getting warmer. The finer the scales we go to, the more noisy the picture becomes, but we still are gradually ticking up in temperature, even when you look at a fine scale place like Central Park. How do we measure the climate? How do we measure weather? So here are some examples. This is some anemometers, some old ones, and here are some modern weather station. And we keep track. We have weather stations all around the U.S., all around New York, and we collect these things together. And as we build up the time scales, we go from having a record of weather to a record of climate. People have been doing this a very long time. The Farmer's Almanac used to be the most tried and true way to know what was the weather or what would the climate be like tomorrow. And it was that intuitive sense, knowing that this time of year, it can be cold, sometimes it's mild, putting together different pieces of the weather and understanding generally what's going to be the climate of the next week or two. And those were the old Farmer's Almanacs. And until we started perturbing the climate system in the last 100 years, the Farmer's Almanac were a very excellent way of keeping track and guessing what was going to happen with the climate system. Now, for the last 40 years or so, we have had satellites that give us a much more complete picture of what's going on in the climate all across the world. This is a special suite of satellites called the A-Train. They're NASA satellites, but they're all together. They're the longest train of satellites in the sky, and that's why we call them the A-Train, because they go the longest distance together. And these have been up in the sky since, in space since 1979. And these satellites and other satellites give us a really broad picture about what's going on everywhere in the world, and it's much more comprehensive, so we can have a much fuller understanding of what exactly is going on with the weather and what exactly is going on with the climate system. Here's a finer look at one particular instrument, the Landsat 7, and it has, this is an older one, 60-meter resolution. Some of the temperature resolutions now have cut down by an order of magnitude, so down to just a few meters, like 6 meters resolution. In places like New York City, and we have this really comprehensive picture of what's going on with our climate system. So that's describing what's happened today and where we're going to go in the future. So here's an artist's rendering of what it would look like to flood Miami, and maybe some people remember that movie from 20 years ago, Day After Tomorrow, when everything got frozen. So which one will our future be like? In order to know that, we use climate models. What are climate models? A climate model is a computer simulation where we break down all the world's oceans and atmospheres, the clouds, the lakes, the land surface, and we break them down basically into little tiny grid boxes. And we know what comes into each box and what goes out of each box. We know how much sunlight comes down from the top, and we know how much energy is re-radiated back out to space. And the climate model keeps track of all of these variables in a way that would be very hard for us to do by hand. And of course, it's global, it's comprehensive. There are many different things that go on within each grid box. Some of these things are very tiny, like clouds, the ephemeral twists of clouds. It's hard to have a discrete picture of what's going on in a cloud when you've tried to break the world down into grid boxes such as this. So we have things called parameterizations that basically explain how a cloud on the whole functions if you were to scale it up to the size of these computer grid boxes. How big are these computer grid boxes? It varies. Most of the climate models have a resolution of around 1 degree latitude by 1 degree longitude. Some are finer scale, but that would say the 1 by 1 degree is pretty standard. If you're on the equator, 1 degree is about 100 kilometers. So that gives you an idea. So these grid boxes here are on the scale of 100 by 100 kilometers. And so we can use this computer simulation to know what's going to happen in future climate. We pump in more CO2, we change the land surface, we change the way we're using the land. What's going to happen? We burn coal, we put the sulfur in the atmosphere, we put more CO2 in the atmosphere. We can make a simulation of what's going to happen in the future. So here's just another picture of what exactly is happening within every grid box and all the different components. Some things we know explicitly. We have measurements for how much water is flowing in the river. We have measurements for how much sunlight makes it to the surface. And some things are implied. It's hard to know like all these atmospheric constituents. Some of them are measured, some of them are implied. Sometimes we have satellite retrievals that tell us something more. If there's people waiting, they can come in.
Excuse me, any chance of getting picture of that, a copy of that slide?
Oh, sure.
Excellent.
I think Mark probably posting this talk. Or
Yeah, I can.
you can talk to me later. You can email me.
Thank you.
So yes, where do I do this? I do this at NASA Goddard Institute of Space Studies. This is the screenshot from Seinfeld. It's actually in my building. And it used to be you could know our computer rooms because these windows were all bricked off because that's where our computer rooms were. We have modern computers are smaller, so we don't these stuff turned back into offices. This is actually what it looks like in my office. People sometimes ask, what does your office look like? What do you do? This is what my office looks like. I have my computer, based on my work. I have all my figures put out together, the paper that I'm trying to write, my kids' picture and some of their artwork to keep me sane, a lot of books. Here's where the chalkboard where I draw out for my grad students and postdocs what they're supposed to be working on, and a map. It always helps me to just stare at my map to try to figure out any kind of perplexing problem. Just staring at the map helps me. So what is there going on actually on my computer screen? So this is very typical for what my computer screen looks like. I have the same command line, this is homebrew color scheme that I was using back when I was a 4th grader at Bonham Elementary in Midland, Texas. It's not a far cry from the Linux command prompts that I use today. The programming that I do, the climate model, is actually written in Fortran. Fortran used to be the most popular computer language that it and C. The climate models are still written in mostly Fortran and C because these languages are extremely, extremely efficient. They're very fast. Kids these days, they like to use Python, R, Java. Sometimes we use these programs for analysis or visualization, but they're just not fast enough. As the old computer programs, when they were written, computers weren't so powerful. We had to really be careful about how much memory we used. And through time, as the resolutions of the model have gotten finer and finer, and all the different dynamics and different physics that the climate system built in has gotten to be more complex, it turned out being this really strategic use of our computer resources is important because it lets us grow a really powerful climate model that can actually run in a reasonable amount of time. There's some visualizations. We have a particular file type that's basically Fortran with some headers on it called .cdf. This is visualizing some atmospheric topography, and this looks like precipitation changes. And so yes, this is basically that my computer used to have mainframes when we run the climate model. Now we use a Linux cluster that's in for NASA. We use a Linux cluster that's in Greenbelt, Maryland. I typically, when I run the climate model, I use about 90 cores, and yes, this machine probably it has 129,000 cores. So a lot of people are doing a lot of runs all at the same time. So in the future, what's going to happen? So carbon dioxide is the principal greenhouse gas driving climate change. And there's this smart guy, Ralph Keeling, who went to Hawaii. He went up Mauna Loa, and he started taking measurements of CO2 in the 1950s. Now, why did he go there? I mean, why did he just, like, he was working as Scripps, why didn't he just step outside? Well, CO2 can actually change a lot. I don't know, like this COVID, like some of us have become more attuned to what's happening with CO2. Maybe some of us measure CO2 in our rooms to make sure they're well ventilated. Do I need to speak closer here? Oh. But CO2 can actually change a lot in your cityscape. Cars, of course, are burning gas and spewing out CO2, so if a truck drives by, CO2 can spike. In the springtime, when everything is blooming, all the plants are greening, all the trees are growing, they can sequester CO2, so they put on their leaves and they put on their green stuff. So right there on the surface, there can be a lot of variability in CO2. In this room where we're sitting, with the outside CO2 maybe at 400 parts per million, but in here, as we're all breathing out, the CO2 might rise up to 600, 800 parts per million. So the reason that he went to Mauna Loa is he wanted to get someplace that was kind of remote, it's in the middle of the Pacific Ocean, and pretty high up, so it would be very well mixed. And so he took this long record of CO2, and even though he went someplace so far, you still see this squiggly around the around the mean line, and that's actually the northern hemisphere growing plants and dying off every season. So in the summer, CO2 drops in the northern hemisphere. Summer CO2 drops a few parts per million as everything gets green and things die off again. It pops back up again. And so when he started measuring this, the CO2 concentrations were about 310 parts per million. But today, we are 100 parts per million higher than that. It is really a big change. In the future, how much CO2 we'll be putting in the atmosphere? Well, we have this coordinated climate research report, that International Panel on Climate Change. We have all these different scenarios. The future isn't set in stone, but how much future climate change is going to happen is kind of up to us. And we have these different scenarios that are basically how we live our lives as a society. How much CO2 do we put back in the atmosphere? Do we decide enough is enough? Do we drop back to a CO2 level that we had 50 years ago? Or do we keep growing at the clip we're going now and pumping it out as fast as we can? So CO2, it does impact the climate system. Some people, depending on the audience, they think, oh, this is newfangled stuff. No, it's not newfangled. Actually, there's this really neat lady, a New Yorker, Eunice Foote. And she, in the middle of the 19th century, she proposed that CO2, Eunice Newton Foote, like, what a science name, right? She proposed that CO2 and water could alter the temperature of the air. She didn't get all the, the details right about how shortwave radiation, like the sun, and longwave radiation, like off of something just emanating heat, worked. But she did get the basics down right. And this was, the 1850s. Later, John Tyndall, he sorted out exactly how different long-wave, short-wave radiation worked, and finally, in 1896, Svante Arrhenius, he proposed that CO2 could actually be responsible for large climate shifts over time. He was somebody who was living in Scandinavia, so he would see glacial moraines, and he was thinking about what could cause these glaciers to come out and retreat back again. And so the idea that CO2 is driving long-term climate is a very old idea. It's just an idea that we have a lot more granularity about how it works now that we have climate models. So in the future, using these climate models, we have made some predictions for how much temperature change there's going to be relative to today. And it's a lot. Like I mentioned, like last year, we were about 1 degree above our 1950-1980 baseline. But these estimates, these are up to 6 degrees above that baseline. That's a lot of temperature change. And you don't always think about it, but temperature and precipitation go hand in hand, because hot air can hold more moisture than cold air. You know that this is true because when you go outside on a cold day, your breath is hot and you breathe out and it condenses into a cloud. So you know, like the warm air of your breath, you have more moisture in it than the cold air outside. And so when you have more moisture hanging out in the atmosphere, you can also have more precipitation. So future climate, we're going to some place that's warmer and also wetter. And there's other things that go along with that. So when it gets hotter, like we've had out west, I know this was New York City last summer. You guys, I'm sure, there was a few days I was taking my kids out swimming and it looked like Mad Max. I was looking, mesmerized by the shadow cast by the trees in the ground. It looked everything in this red hue. And that red hue was because we had fires out west and the smoke had drifted all the way, 3,000 miles across the US to impact us here in New York City. Now those fires were happening, it's hotter temperatures. When things are hotter out there, it tends in California to get drier. And you're closer to the flash points and fires when they get going. You can have people pulling more air conditioning, transformer fires get started, and things just get going. And we've had these huge fires out west now a lot of years. And so you sometimes don't think about it, but these other kind of compounding factors come in as part of climate change. So this is from our latest Intergovernmental Panel on Climate Change report about what's going to happen in the future. These are kind of stylized maps of North America, South America. Australia, Africa, Europe, and Asia, places are going to be more susceptible to drought. Almost everywhere is going to be more susceptible to extreme heat. And also, we're going to be more susceptible to extreme rainfall. So people, I don't know if folks remember, like maybe 5 years ago, there's all this talk about the Oroville Dam in California is going to fail. This is the Oroville Dam when it's about to fail. You see it's overflowing with water. Atmospheric rivers were hitting this place. And then last year, it was the opposite. The newscaster is talking now like California's in dire straits, like they're desperate for water. And so these wild swings from very hot to very cold, like this is kind of part of what's going to be happening in future climate change. And this even happens here in New York City. This is kind of in my neighborhood. Like, I don't know, these people who want to wade through the subway in the water, I wouldn't have gone in there, but some people had to get where they're going. And we actually had 3 of these record-breaking storms. This is the, I pulled this from the Yonkers Times. This is the Spring Parkway. People's cars are inundated. 3 times last summer, we had these insane storms just dropping so much water on us. And this future where we can have more extreme rainfall, this is part of what's going to happen in future climate change. So we have these climate models. They've made some predictions, but how do we know these climate models are accurate? So I'm going to kind of take a step to the side and talk a little bit about the context, putting these things into context. So one of the main things I research is past climates. Why are people interested in past climates? I told you I got interested in past climates because I saw how civilizations could be made or broken by climate change. So there's an academic component to it. Also a possibility, like a dreamer. Like we don't, like the last 100 years is not representative of how extreme and how varied the climates have been on this earth. So past climates are important in understanding all the different modes of and types of climate that can happen here on Earth. And it's also a way to evaluate my climate model skill. I can try out my climate model on a past climate, and I can have records of that past climate, and I can see if my model is any good. Oh, past is prologue. Oops, I had 2 of those slides. Sorry about that. So one easy way we can see about climate change is like that Svante Arrhenius talking about how maybe CO2 is causing big climate changes. And we can see these kinds of climate changes, glacial retreats, all around the world right now. People in California, people looking at the Cascades, people in Norway, people all around the world looking at their mountain glaciers retreating. And we actually, because this is the age of these retreats have happened since we've had photography, you have a lot of examples like this, where you see a picture from 100 years ago, a nice, healthy-looking glacier, and then you pump through until the present day, and these glaciers are retreating. So that's one way we can get a record of what's happening with climate change. If we want to get more specific records of climate change, we often go to places like the ocean or to lakes. This is me when I was young, working on an ocean vessel. Turns out that in the ocean, the layers of silt that are deposited, they're little tiny zooplankton that live in the ocean. And as they're living their lives, they are taking a snapshot of what's going on in the ocean climate, where they are growing and thriving. They're building their shells. There's corals that do much of the same thing. Ostracods are a similar kind of species that lives in lakes. And then they die, and then silt is deposited on top of them, and more grow and more die. And so if we go and we take a sediment core, we can have a record, a fossilized history of what the ocean climate was like over time. And so this is one of the methods we use. Another is like ice core records. Ice cores are really neat. They have a record of snowfall in a place, but it's not just snowfall that we can get from ice cores. The atmosphere, snow when it first falls, there's a lot of spaces in between, but as the snow gets heavier and heavier and heavier, it compacts down, and little bubbles are frozen in time. And so we can have fossilized bubbles of ancient atmospheres when we retrieve these ice cores. Now, paired with the ice itself, it turns out temperature impacts water molecules themselves. And so we're able to tell how temperatures and old atmospheric concentrations of CO2 went hand in hand. Speleothems, this is a cave deposit, like stalactites, stalagmites. It's also made of calcium carbonate, just like the shells of the foraminifera. And these also have a record of the same like water molecules. The oxygen molecule comes out of the water, comes into the calcium carbonate of the cave deposit and the calcite, and we have a record of climate change in cave deposits as well. And when we look back through time, so this is a very typical picture you see. This is a speleothem record. It's a speleothem. Here's a temperature record from an ice core, and you can see by the water itself, the ice, and this is the oxygen atom from the carbonate, the calcium carbonate or the calcite. These are related to temperature, they're related to precipitation, and so we can have these very long records of how temperature and precipitation were changing through time. The aragonite shells from the corals, they can tell us not only that oxygen atom is in there, so we can tell a little bit about the temperature of the ocean, but also corals have a really specific environment where they grow. Some corals like to grow right just below the sea surface, and some grow a little bit deeper, and so we can tell based on what species we find. Species, they're not fossilized species, they're no longer living. We can tell how deep the ocean must have been to have this particular kind of ocean of coral living there. And so we have long records also of sea level change through time. Now, when we put these all together, the first thing that pops out is that small changes in the Earth's, these are all supposed to be videos. Only some of them are playing, sorry. We can tell that the Earth's orbit around the sun, its eccentricity is changing. The Earth's orbit is elliptical around the sun, but there's been times in the past when it's been more circular. And there's a phasing between the precession, vernal equinox, which we are coming up on right now, when the days are the same, you're halfway between spring and summer, and the phasing between that vernal equinox and if you're on the long side or the short side of this ellipse can influence how much sunlight makes it to Earth's surface through time. And the last piece is obliquity, which is how the Earth is tilting on its axis. This was figured out in the 1930s by Milankovitch, and these are called Milankovitch cycles. So when we look at these long records of climate change, the first thing that pops out are these cycles. But if you look at records that are older than 500 years, this is definitely what pops out. If you look at newer records, especially records from the last 200 years, we have broken down this cycle. So as a truth test, let's try to think about when was the last time that climate was as hot as it is today? And this is a question, like in January, sometimes like climate scientists, we all get these same calls in January. They come out with a temperature, last year we were 1 degree Celsius warmer than our average. When was the last time it was so hot? And the truth is, in the last 10,000 years, basically since humans were humans and we had agriculture, we were not this hot. So this purple line is how hot we were. This is a trend for the last 11,000 years about, this is years before present. It's starting 11,000 years ago, come to the present. This line with purple and blue is how the temperature has changed. This purple line is where we are today. And you can see, since humans had agriculture and humans' cultures and societies were what they were, we have never been this hot. So we want to dig back deeper, go back deeper in time. You go back further in time and all of a sudden you have ice sheets growing, ice sheets shrinking. We have records of ice sheets growing, ice sheets shrinking. This is a record from the last 800,000 years. There's CO2 on this axis, temperature on this axis is the reddish colors, and CO2 is the bluish colors. We can see these two things from the ice cores going hand in hand. Ice sheets are growing, ice sheets are shrinking. We pull back in time before the last ice age. the previous Holocene-like period, called the Eocene, or the last interglacial period, about 127,000 years ago. This point in time, these graphs are kind of complicated, but basically what they're telling us is that the ocean temperatures at that time were about the same as ocean temperatures are today. So here we have an analog for where we're at today. But here's the weird thing. Sea level at that time was 8 to 9 meters higher than today. That doesn't sound like a lot, but Battery Park would be toast if sea levels were 9 meters higher. 9 meters is like 30 feet. I mean, this is a substantial increase in sea level. We would be okay here in the Hudson River Museum, but the shore of the Hudson River would be closer to us. And a lot of the communities that have grown up right along our coastlines would be gone. And so we know the analog for temperatures as they are today is for sea levels to be higher. And so the question, like future sea level change, it's coming. The question is not whether or not it's coming, it's like how fast is this coming? How fast can the ice sheets respond to the temperatures we have today? But in the last glacial period, interglacial period, CO2 levels were much lower than they were today. They were pre-industrial levels, 280 parts per million. Remember, today we're like at 410, 415 parts per million. So if we want to know an analog for the last point in history that CO2 levels were as high as they were today, we have to go much, much further back in time. We have to go to a period called the Miocene to get to an analog of today. The Miocene is like 15 million years ago. And if we want to an analog of where we're going to be in 100 years' time, if we keep on pumping out the greenhouse gases, we can go back to a time when carbon dioxide levels were much, much higher, a period called the Eocene. The problem is as we go and we push our records further and further back in time, Earth was a very, very different place. The continents had different configurations. And so we're in a pretty different state than we are today. So if we pull back and we just look at the Pliocene period is, so here, the Pleistocene is where we live today. The Pliocene is the one right before that. Pliocene CO2 levels were up to 400 parts per million. And just try to think about this, maybe this, like once everything, the temperatures respond, we get into equilibrium. Maybe this is our teleo analog. So in the Pliocene, temperatures were warm by several degrees, and sea levels were 22 meters higher than they are today. This looks like a global map, but if you look carefully here, you'll notice like Florida's missing, and it was pretty different. 22 meters of sea level, like that is a lot. That is a lot of sea level change. So the equilibrium conditions the last time the Earth had 400 parts per million of CO2 are much higher sea levels. And if we keep pumping CO2 into the atmosphere, like what is the future? Well, this is like when you go back to kind of exotic times, like the Eocene, 55 million years ago, we had crocodilians living off Svalbard up there in Norway, and we had tropical forest in places like Utah, and we had palm trees in New Jersey. It was a much different climate system than we have today. There were no ice sheets back in the Eocene. All the ice sheets in Antarctica and Greenland that we know today, they did not exist. And it was a very different kind of climate system. So this is probably not something we want to experiment with. So all of those, like as analogs, is interesting, but it's also a way to truth test our model and to know like how well is our model doing. So the way we do that, so I have, this is our simulations for my climate model. I have simulations for the last glacial maximum. These are simulations I typically run. I run simulations from the present day all the way back to the Eocene so that I can cover a broad range of temperatures that are both cooler and warmer than they are today. And I truth test the model. I see how much CO2 changes there were in the model, how much surface air temperature changes those resulted in, and I look at those past climate records and I say, how well is my climate model performing? Is my climate model able to estimate an appropriate scale of temperature change, even though these climates were very exotic? And the answer is yes. The climate models are getting these basic these basic phenomena related to how much CO2 in the atmosphere, climate models are quite good at matching that. So, for the future, we hear a lot of talk about, let's try to keep our future temperature change at 1.5 degrees. Let's try not to make it 2 degrees of temperature change. So what kind of a difference is half a degree? Right now we're already at 1 degree. What kind of a difference is a half a degree? It has a big difference in the number of heat waves you can have, a big difference in the amount of moisture in the atmosphere, so the extreme kind of rainfalls that you're going to have. Crop yields will be much more consistent if we are growing crops where we design the crops to grow, where we and our sea levels can be mitigated if we're just careful about keeping the temperature changes. We want a climate that's habitable for people, and so keeping it as close as possible is the best option. So what can you do? This is a video clip that I thought sometimes, some of these cartoons are very insightful. This is from Futurama. What do we do? This is explaining like greenhouse warming. What can you do? Well, is this important to you? You're here today, so obviously you want to educate yourself. The next thing that you can do is let people who represent you know the things that are important to you. So in New York City, there is who represents me. You can find places like NOAA. They have ideas for how you can cut down your own CO2. Here in Westchester, I was looking for some place like who represents me. If there's an equivalent site in Westchester where you could just type in your address and find out everybody. I couldn't find one, but there is this USA.gov where you can go and find out all the different people who represent you, or the League of Women's Voters. They'll also help you out. You can continue to educate yourself. In the US, we have programs like the Climate NASA Gov, Globe.gov, Climate.gov. These are all partnerships with between the public and NASA and NOAA, which is the National Oceanographic and Atmospheric Administration. So educating yourself and letting people who represent you know what is important to you. These are some of the most important things that you could personally be doing every day. There's also a sense that what can I actually do in my everyday life? Like what's the most effective thing that I can be doing? So this is a figure that came out a few years ago, talking about what personal choices, what kind of impacts these can make. This is funny on the end. This is how much having one less child. This is not really meant for that. I think they did that so they would have some sort of huge like news blitz because it sounds radical. But this is just basically how much one human, how much CO2 in North America is burning through a year. So the different things that you can do that have a meaningful impact on the climate system. Living car-free. This is tough to do or easy to do depending on where you live. Avoiding one transatlantic flight. This is probably one of the easiest cuts. We all made this cut during COVID. Like thinking about strategically like how you get around and how the things that you consume get around. So the goods you're consuming, are they brought to you by plane? Are they brought to you by boat, by train? Consuming more local goods. And then it goes on down like eating vegetarian, switching to an electric car. And finally, at the very bottom, upgrading your lights, good for your electric bill, not such a big deal for the climate system. So this is for the U.S. Where are all the greenhouse gases coming from? So you can go, I'll give Mark a copy of this so you guys can have resources if you want. Energy use in buildings, your transportation sectors, energy use in industry. You can go and look up like where things are where CO2 is being consumed. And this is why it's so important to know who represents you, because most of these things are outside of your personal control. So it's good to change your light bulbs. It's good to avoid those flights if you want to reduce your CO2 footprint. But talking and thinking about how to reduce these bigger pieces of the puzzle are equally important. And these can only be done by people who represent you and by people who are building up these industries and the way we connect ourselves in society and culture. Okay, so yes, there's actually kind of a schism in the climate researcher community. People like friend Ken Cobb, who say we're going to, not only are we going to contact our legislatures, we're going to stop flying. And there's other people, another scientist here who thinks that personal actions don't matter less, it's more important to fly around. I think it doesn't hurt. I mean, I fly less than I used to. And I also, I know who represents me. And those are both equally important pieces of the puzzle. So there's more reports. I put these in here because I'll give Mark a copy of my slides, just so you can have resources about who's using these resources. This is the different carbon measures, industrial emissions, and like which companies put out the most CO2. You can use this information to strategically talk to people who represent you, or think about the companies that you are associated with. And one of the big inequalities of the world is that we talk about this global world, and it's the whole world who's having to deal with the fallout of climate change. But truly, the richest 5%, like they're doing almost all of this, and this exponential rise here scaled generally as you get richer and richer. So the wealthiest people, the wealthiest countries, those are the ones burning through the most greenhouse gases. As for us in New York, the future, what are we going to do? How are we going to adapt? How are we going to mitigate? There was an idea floated about building a floodgate across the Arizona Narrows to harden us against storm surges in New York City. Is this the right option? Building less on the coastlines, building more on the coastlines, building buildings that are hardened against sea level rise. These are all kinds of thoughts and questions that we should be thinking about and discussing with the people around us. So sometimes I get to the end of my talk and people say, "Oh, that was very depressing, Allegra." So my friend Christy Dahl, she also got this comment, and so her friend here, she wrote this blog piece for the U.S. Union of Concerned Scientists, and she says, I don't have some hopeful gospel to preach to you. I'm not even going to encourage you to be hopeful, but in wandering a path from climate awareness to climate anxiety to climate anguish, and learning something about the true nature of hope after all these years, I say, when people think of hope personified, it's usually a butterfly or a dove or a sapling sprouting from the ground. Yes, it's all that, but that's not the hope we're talking about to address climate change. In Finland, there's this word sisu, which gets crudely translated as determination, grit, and courage. So hope is a discipline for survival, and let's call it love. I'm not sure they're different, and therein lies hope's unstoppable power. If you love anything and you hope, and each of us working to add our small piece to the whole, many of us weary of all this, but cloaked in our miraculous hope. When despair can touch us, but it can't hold us for long. Because we love, and therefore we hope, and because this fight is far from over, it starts new each day. But the fight for our earth is also everything. And you, my weary friend, will never stop. That's by Erica Spenger-Siegfried. And so don't be hopeless. Be hopeful, get out there, and raise your own awareness. And that is the end.
Okay.
Yes.
Yep.
What's happening I'm curious about what's happening on a global scale as far as your involvement or NASA's involvement with other nations, things like that.
So on a global scale, we have this thing called the Intergovernmental Panel on Climate Change. And my piece of that is this massive document that's produced every 7 years, and it's broken down into 3 parts. The first part I work on is like understanding the climate system, what it was in the past, what it is today, where we're going in the future. Part 2 is the impacts group. How are these climate changes going to impact agriculture? And then part 3 is what are we going to do with that information? Or how are we going to harden against? So there are people who specifically focus on how are we going to mitigate against climate change, how are we going to cope with climate change. That's not a part that NASA is involved in as much, but the resources that NASA provides is in understanding what's happening today, and characterizing what's happening today, and predicting what's going to happen in the future. So we are research partners and a resource of information, and so I would say NASA is on the side involved, maybe not centrally involved, especially not in making regulations.
Thank you.
Yes?
I thank you very much for a very clear presentation. I understand the impact of CO2 and how your model is tracing that. I'm just wondering, and knowing that Foote came up in the late 1800s, when do you start talking about all the other geological eras,
Mhm.
and speaking with such knowledge of what is happening? Where did the science come from to get that kind of specificity of what it was like millions of years ago?
Oh, how do we know?
Yeah.
So, remember I talked about these special oxygen atoms. They start out in the water and then they get recorded in things like calcite, calcium carbonate, CaCO3. It's actually like you can determine in the lab in the oxygen, like isotopes. If you think back to your high school chemistry class, isotopes means that you have more neutrons, and it changes how much of these ones with extras, these heavier isotopes, are incorporated into calcite. That changes based on temperature. And so by measuring how much of the heavier isotope, how abundant that is, we have a record of temperature through time for those ocean records. For ice core records, it's something that's more empirically derived. They actually have to calibrate how the concentration of those heavy isotopes correlates to temperature. They have a record in ice, and then they have a borehole measurement where temperature diffuses through the surface at a certain rate and diffuses through ice at a certain rate, and so they calibrate this way. So we know based on the borehole temperatures how cold it must have been at the last glacial maximum, and we calibrate that to what we have in our the isotope records in the ice cores, and that's used to calibrate these proxies of past temperature change. And there are other proxies like that some of them are empirically derived, and some of them are they're like lab studies. It's just something. It's just those are the ones.
That's pretty new science that's coming up.
I would say like the ice cores, like that science was developed in the 1960s, and how the heavier isotopes get incorporated. That was something that was really understood well by the 1950s. So it's new-ish, but it's a field that's been around for 70 years, so it's pretty mature.
Thank you.
Yes.
I'd like to share some of this information with the youth group. Is there a scaled down version or one that's geared towards a younger age level?
Oh, I've given a talk for middle school kids before. You can reach out. We also have we had education officers at NASA, so feel free to reach out to me, and I can pass you on to our education officers. NASA has resources. We also have special programming for younger audiences too.
If you don't have cards, I can give you one of my cards.
I'm sorry, I don't have cards. Let me go back to the first slide. My email is very easy. If you know my name, it is my name at nasa.gov or at columbia.edu.
Actually, there's one little thing I wanted to point out, which is kind of neat. So you were talking about how when Keelan started doing his studies in Hawaii, there was about 310 parts per million.
Yep.
And now it's about 410 or
Yes.
plus, right? I just want people to understand how much of the atmosphere that is, because a lot of times you hear people say, humans couldn't really affect the amount of carbon dioxide in the atmosphere. So everybody do this. Hold your hand up and spread your hand out like that, okay? Now imagine that you drew a circle all the way around your hand, from the tips of your fingers all the way around the base of your palm. Imagine that as a pie chart, right? That pie chart is gonna be the makeup of the atmosphere. So what that means is that if you go from here to there, all the way around the circle, in other words, more than 75% of the way around the circle, that's nitrogen. So every breath that you take, most of it's nitrogen. This little wedge right there, almost all of that is oxygen. And then maybe like half of the thickness of your finger is a gas called argon. Now here's the thing. This, and that do almost nothing to retain heat from the sun. Basically, light goes right through it, infrared goes right through it, goes right back out into space again or whatever, okay? The stuff that makes the difference between the Earth being, 30 degrees below zero and being 70 degrees on average, roughly, is essentially, what's the figure, right? 50, sorry, not 50. 50. It's a layer which would be, what would be about that? Like a layer of spaghetti, maybe?
0.04%.
0.04%, yeah. So yeah, picture like you take a piece of linguine and then you shave it until it's about half that thick, and then you glue it to one of your fingers. Okay? That's what's making the difference. So if we've increased that by 20, 30, 40%, it's a huge difference. So whenever somebody says, oh, we can't have done because it's such a small part of the atmosphere that makes a difference, if we've changed it a lot, it makes a big difference to the Earth overall. I just wanted to, just in case,
And
I
that
want to make sure
sliver
people
is
get
CO2?
that. Sorry?
That sliver is CO2?
That sliver
CO2.
is CO2.
CO2. The other really important greenhouse gas is there's the ones like methane and N2O, but water is an important greenhouse gas. And water can be super highly variable. We know this. It rains, it's dry. But once you start warming it up a little bit, it gets more water. And so water vapor in the sky reinforces these changes that we get from CO2. I think I forgot to mention the numbers, but the context, like the last glacial maximum, this was about 5 degrees colder, and the CO2 concentration was about 180 to 200 parts per million. By the pre-industrial, we're up to 280 parts per million, and it was 5 degrees warmer. So that shift of 80 to 100 ppm of CO2, that made ice sheets cover New York and wane again. It made sea levels retreat back 120 meters and come back to where they are today. Just by that change. And we've already eclipsed that glacial to interglacial change in CO2.
So we need guano.
Well, we when there's catastrophe coming, if you get on top of it early, sometimes it's a small flick can avoid that catastrophe. The longer you wait, the bigger the push is going to have to be to change us from that course. So sooner is better.
So ever since I've been alive and hearing about climate change, half of what I'm hearing is people don't believe that it even exists. Are you finding that that's getting a little better? Or
So, I mean,
No.
I think that the denial has changed. I mean, I think if you were to survey people by age, you would find that people under 30 generally are, no matter where you are in the country, they're like, yeah, we understand, we get it, in a way that people who have maybe set their belief systems already are less likely to. But I mean, even my parents' friend, my father's in the oil business. I hang out with them. Most of them, yeah, they believe in climate change. They have to, like they know. Like if you ask somebody like, oh, how old is the field that you're working? Oh, this is the field from the Miocene. This is the field from the Eocene. They know what the climates were like in those times because it is the flora and fauna that were converted to the hydrocarbons that we're consuming today. I mean, it was kind of like this great chemical battery that was done back then. The CO2 was sequestered in their bodies, and it was storing this like heat energy that was going around the atmosphere from the sun and taking the carbon dioxide in, and it's this chemical battery. So in a way, we're relaxing back to those climate systems of the past when those deposits were formed. So the denialism is more like, not having the willpower to want to change. It's, I'm rich, and we know that rich people are probably going to be okay. Like, if my cost of milk doubles, I can handle it. It's not my house that's going to be flooded, so there's that. But I think that the outright denialism that just doesn't exist. There's less of that than there used to be. Yeah.
The receding of the glaciers, and I guess in Siberia, methane is being released from the ground as there is a retreat.
It's complicated, yeah.
It seems like even these little things that can be done, this is so vast what's happening at the Arctic and in Siberia that, you know, you wonder why there isn't a more massive effort on the global elite and the organizations to really, it's an existential crisis. And I don't see anybody addressing on it on the scale that it should be.
It's hard. It's hard. Even in a place amongst believers like New York, like, you know, I before COVID happened, I was commuting to bike by work, commuting to work by bike, excuse me. It was not that easy to commute to work by bike, even in New York City. Like you know, it's much easier. Like if I were to drive to work, my commute would be safer, it would be faster, and probably more pleasant. Because it's a big change in the infrastructure, and there is a feeling like, you know, are you taking away from someone else? And people who are accustomed to their system, nobody wants their stuff taken away. So it's hard. We're gonna have to make hard choices. And yeah, so that who represents me page, go find that. Go find out who represents you. It's easier to start local with people you might encounter on the streets every day, then you can work your way from there.
Thank you.
If there's no other questions, then
I think have a naive or silly question.
Oh, sure. Okay.
When I first saw Al Gore's presentation, how many years ago, you know, the talk at the time was by 2050, we'll be on the tipping point, there'll be no coming back. Has that escalated? Where are we in that perspective?
My old boss, Jim Hansen, used to talk a lot about tipping points and, you know, how we started this ball rolling. I mean, as far as the paleoclimate analogs are concerned, I mean, we know how much ice sheet has to be melted to be consistent with the global temperatures as they are today. We know. So the tipping point is really, it's like, how much are we willing to accept? Like, how fast climate is going to change, how fast sea level is going to rise, like, how much are we willing to accept, to adapt to? Like, when will there be that magic point where it becomes more expensive or more harmful or more unacceptable to deal with the actual repercussions of climate change than it will be to, you know, build out the systems that we need to put in place so that we can avoid it. So
Has it been escalating at a faster rate than we anticipated?
has sea level been rising faster than anticipated? No. There's a lot of
or global warming.
Warming. The climate models have actually been pretty consistent. I mean, much of the uncertainty comes from, like, you know, how much CO2 are we going to be burning in the next decade? Like, it looked like we were carrying on for like RCP6. That looked like what we were doing. Not the worst, most extreme scenario, but the next one down from that. But things can change. Gas prices are high right now. Maybe we'll have a point. We'll decide, like, hey, maybe we're going to reduce our energy usage because we don't like this.
Mm-hmm.
So we don't know which trajectory we're going to go on.
Mm-hmm.
But as far as, like, climate models knowing what is the impact of CO2, they've gotten to be pretty decent at that. The thing I didn't talk about that has a big uncertainty around it is aerosols. Mm-hmm. So sometimes some things like coal, they produce not only carbon dioxide, but also SO2, which becomes sulfate aerosol. And that works against climate change. It reflects the sunlight, and so it mitigates against climate change. It's not all a good thing. Plants actually need sunlight to grow, so you can have decreased plant crop yields if you have too many aerosols. It's bad for human health. So it's just, you know, understanding exactly how our aerosol emissions, how our CO2 emissions are going to change through time. We have some natural case studies, like when COVID first happened and all the factories shut down. You saw pictures from around the world for how basically the aerosol component was getting taken away because of that factory reduction was shut down. Aerosols have a pretty short lifetime in the atmosphere. They only last like a couple, 3 weeks. So you saw, like, as these emissions that turn into those aerosols were reduced, March 2020, April 2020, you saw basically a clearing of the skies around the world. And we can, the climate models, like something we're actively working on, this natural experiment that happened across the world and how, the relative impacts of the aerosols on the climate system. The thing is, like, CO2 though, it lasts so long in the climate system, it doesn't have a half-life of, 1 to 3 weeks, it's a half-life of, hundreds of thousands of years. So the CO2 that gets put up in there, it may not grow as fast. It did not, in fact, grow as fast, CO2 emissions in the world in March and April 2020, but we overcompensated for it. So we kind of had this little pop back up again. But that little hiccup, it didn't impact how much CO2 was in the atmosphere in a meaningful, lasting way. So the models are pretty decent. It's about understanding what the emissions are going to change in time, more than the first principles of how well the climate models are actually guessing at or predicting how the climate system should go.
Thank you, extremely knowledgeable, appreciate it.